In this section, we're going to talk about optimization problems. In optimization problems, we are asked to find an absolute minimum or an absolute maximum that gives the best value for some quantity, in other words, the optimal value. For example, you might want to find maximal profit or minimum cost. Let's see an example. One model of a flu outbreak predicts that the number of people ill, N of t, with the flu, will be given by N of t equals 90 plus 9/4 t minus 1/40 t squared, where t ranges from 0 to 120 inclusive. And t equals 0 corresponds to the beginning of December. On what day will the flu have reached its peak, and how many people will have the flu on that day? I don't know if we would call that the best value for the flu, but anyway, we're being asked to find the absolute maximum of the number of people that have the flu. So we're going to just basically go with our procedure for finding absolute maxes and mins. We need the derivative of our function. So let's see, the derivative of 90 is 0. The derivative of 9/4 t is 9/4. And then for minus 140 t squared, we have 2/40 t. In other words, we have 9/4 minus 1/20 t. That's never undefined, so we don't have the undefined kind of critical point. If we did, we'd need to check it. But we can set this equal to 0, which will give us 1/20 t equals 9/4 if I add 1/20 t to both sides. And then I'll need to multiply both sides by 20 to isolate the t. That gives us t equals, oh, and let's cancel. The 20 cancels with the 4 to give a 5. So I have 9 times 5, which is 45. So we're guessing that at this point it's looking like the peak of the flu season is probably 45 days in. But remember, critical numbers don't necessarily give a max. They might give a min, or they might give neither. So how are we going to determine that? Well, because the stated domain of the function is a closed interval, so I could write that domain for t is 0 to 120 like that, with the square brackets indicating it's closed. We can use our closed interval method for finding absolute maxes and mins. And the way the closed interval method worked is here's just a quick review of that. Closed interval method for absolute maxes and mins. When we find critical numbers that are in the closed interval, which we've already done, and 45 was definitely in our closed interval from 0 to 120, then we evaluate the function This is the function to be optimized, not its derivative now. That's a classic mix-up that people do, is to evaluate the derivative. So not its derivative. At the critical numbers and at the endpoints of the interval. And then for your conclusion, the largest value, the largest function value is the absolute max on that interval, not necessarily anywhere else. And the smallest is the absolute min. Okay, so we did this in, I think it was section 3.1 if you want to go back and look at that. But here's a review of how it works. Okay, so here we go. Step 1, we already did. The critical number is t equals 45. Step 2, I'm going to evaluate the function n of t, not its derivative, at 45. So let's see. N of t was 90 plus 9/4 t. Minus 1/40 t squared. And just go ahead and use a calculator for this. And I'm getting about 141 if you round off to the nearest person. I'm actually getting 140.625. Okay, now we evaluate at the endpoints. The endpoints of our interval were 0 and 120. So plugging in a 0, I have 90 plus 9/4 times 0 minus 1/40 times 0 squared. That's going to be 90. And n of 120 is 90 plus 9/4 times 120 plus 1/40 times 120 squared. And I'm getting 0 people with the flu at day 120. So we can see that the absolute max, which is what we're being asked for in this problem, is the number 140. So we can conclude that the peak of the flu season occurs on day 45 with 141 people ill with the flu.